Okay, hello everyone. I will talk about rule-based optimal control for autonomous driving using CLF and CBF. So here will be the content of the presentations, and I will briefly talk about how I implement the paper, the portion part, some specific findings of the paper. So this paper implement an optimal control approach for an AV to navigate on the road, as you can see in figure on the right. There are several examples in the paper. But in short, the paper, all the constraints will be formulated as CLF and CBF, and also some iterative rule relaxations will be formulated according to the priorities of the rules. So I will try to implement this paper, but I will focus on the CLF, CBF, and the recursive rule relaxation algorithm. And this is the CLF general form, as you can see on the equations. Based on the affine control system defined above, and we have some CLF slack variable that ends the epsilon tuning constant 12 that we can tune later, and these are CBF functions and also the HOCBF functions equation that we will need to compute the CBF later, and delta I here is just CBF slack variable. And then we will formulate the problem for this optimal control problem. The dynamic model here is chosen, we just only consider the kinematic aspect of the vehicle, and the cost function is just in quadratic form, which consider the Euclidean norm to all the control input, longitudinal velocity and angular velocity or steering rate, and all the slack variable for the CLF and CBF. So that this cost function will decide the trade-off between the CBF relaxations for trajectory checking or for the CBF relaxations for the avoiding the unsafe set. And also we will regulate we will impose the regular state and control constraints at other regular optimal control problems. We also impose the terminate constraint to make sure that our vehicle can reach to the target goal. So for CLF, we use CLF for the trajectory tracking of the vehicle. So the vehicle will follow this reference trajectory. And in order to do that, we will choose the Vx, like is the arrow like this. And from this function, the Vx, we will compute based on the definition of CLF to get the CLF constraints. And for CBFs, we will have three conditions: the pedage avoidance, the lane keeping, and the minimum velocity. So for different conditions, we will choose different CBF Bx functions, and from the definition of Bx, as in previous slides, we will compute the CBF or the HOCBF constraints, as you can see on this slide. For the priority structure algorithm, we will iterate or hold the power set we create from only three rules: O1, O2, and O3. In which specify which CBF will be relaxed in the priority order, and the recursive relaxation algorithm are written in pseudocode, as you can see on the right on the slide. So for the simplifications of the paper, so the paper use QP, but we will use SQP and optimizing the whole trajectory using FPinCon in MATLAB, and we will of course employ different dynamic model and control inputs. And so the CLF and HOCBF equation will be structured differently following the dynamic model. Now, in the paper, the priority rules framework have 8 rules, but we will scale down to only 3 rules, so that we will simplify the implementations. And of course, the equivalent and the optimal disk coverage are not considered in this project. So for the tuning parameters, select different appropriate hyperparameters. Epsilon and gamma is extremely important because they directly affect the performance of the controller. So for example, if we increase the gamma in the pedestrian avoidant HOCBF, we can see that like it change the optimal ego vehicle trajectory change drastically, and also inappropriate values of hyperparameters can also render an infeasible solution. So for the result, we were testing 4 scenarios here. No CBF constraint are relaxed, a lane keeping constraint is relaxed, pedage constraint is relaxed, and both lane keeping and pedage constraint are relaxed. So for the first scenario, all the constraints act as half constraints, so all the slack variable for all the CBFs are 0. And you can see the vehicle follows a path between the gap of the lane boundary and the pedestrian safe circle. For the second scenario, we relax the lane keeping constraint, and the iterative power set will find the optimal trajectory when lane keeping is relaxed. So you can see on the left, the lane keeping constraint is violated, but it's still not violate. It does not violate the pedestrian and the minimum velocity constraint. And you can see that the lane keeping slack level has the negative value, but only when the constraint is violated. So this third scenario is pretty much similar to the second scenario, but we for testing purpose, we will try to enforce the lane keeping and relax the pedestrian constraint. So you can see that like the trajectory violates the pedestrian safe circle, but because there is no other feasible trajectory in this scenario, but it tries to stay as far away as possible from the pedestrian to minimize the constraint violations. And you can see that the pedestrian distance slack level is negative, so it's signifying that there is a constraint loosening here. And for the final scenario, we assume that the vehicle is initially outside the lane, and the pedestrian is standing close to the vehicle. So in this case, both lane keeping and pedestrian constraint need to be relaxed at the starting point, and we can see that the vehicle tries to move out of the circle of the pedestrian as fast as possible, as you can see on the green optimal trajectory here. However, the vehicle tries to exit the pedestrian circle, but also it tries to go inside the lane as soon as possible to minimize the constraint violations. So thank you for listening to my presentations, and here's all the reference I use in this project.